Hey, you have made it to part 3. I need to grab some markers again, of course. Never get anything ready until it's after the time to start. Okay, this is part 3 of this exploration, and now we're dealing with Diophantine equations. Hopefully you looked at that little image I posted from my number theory book that gives some little crazy story about how old Diophantus was when he died, and hopefully you wrote an equation and figured that out. But anywho, so now these are what we call the Diophantine equations. And they are equations of the form ax plus by equal to c. A, b, and c are constants. So there's going to be numbers for a, numbers for b, numbers for c. And we are finding solutions x and y. So it says solutions are a pair of integers, x naught, y naught. When I use little subscripts, I'm just saying this is a particular value, right? X and y you can think of as kind of variables, and x sub 0, y sub 0 is a particular solution, even though I haven't told you what x sub 0, y sub 0 are. So they have to have integer solutions. First example right here, 3x plus 6y equal to 18. I'll stop for a second, and can you think of any integers, x, y, that satisfy this? Maybe I'll say one solution is x sub 0 equal to 6, y sub 0 equal to 0, right? Clearly you could do x sub 0 equal to 0, and y, I'm going to say x sub 1, y sub 1. What would y have to be if x is 0? And that's right, 3, right? And if I was to list out more, the next one I would list out would be x sub 2 and y sub 2. So a lot of solutions there. How about this guy? I'll be quiet for a minute, but can you think of an integer solution to 2x plus 10y equal to 17? What's that? No solutions. No integer solutions to this y. Okay, because anytime you put an integer in for x and an integer for y and add them together, you're going to get an even number. Good. So it turns out that if you can find one solutions, there are a countably infinite number of solutions. If there's no solutions, there's no solutions, right? Okay, so let us, how in the world do you say does this relate to what we've been doing the last couple days? Well, let's find out. First off, it says that ax plus by equal to c has integer solutions only when the greatest common divisor of these two numbers divides c. Divides, remember, means that it's a multiple of that number, right? It'll divide it evenly with the remainder of 0. Okay, so we look at this, and what is the greatest common divisor between 20 and 14? It's 2, right? And so 2 certainly divides 2, so this one will have solutions. But how do we go about finding the solutions? We use the Euclidean algorithm, surprisingly enough. Okay, so we are going to look at the greatest common divisor of 20 and 14. To do that, remember we took 20 and we divided by 14. 14 goes once in, and we have a remainder of 6. Okay, and so then the next step in the Euclidean algorithm was to take the lower number and set it with the remainder. And so we want to find the greatest common divisor between 14 and 6. So we're going to take 14, we're going to divide it by 6. It's going to go in twice and have a remainder of 12. A remainder of 2, excuse me. And we do it again. So we take the lower number, greatest common divisor of 6, and now 2. And when we divide 6 by 2, it goes in evenly. That is, we do not have a remainder. And so remember then greatest common divisor is 2, and we're going to go backwards from this. We are going to write this equation. What did we do here to get 2? What did we do to get a remainder of 2? Well, we had 14, and we subtracted 2 6s from it. So I'm going to write 14 minus 2 times 6. That's the equation we used, okay? And then we're going to go back to this one. And here we got a remainder of 6. But how did we get a remainder of 6? Oh, we did 20 minus 14 to get 6. So we're going to go replace the 6 with 20 minus 14. So I'm going to write 14 minus 2 times 20 minus 14. And now I'm just going to rearrange things a little bit. I'm going to distribute this minus 2. So I'm going to end up with 14 minus, and I'm going to write it as 20, 14 minus 20 times 2, and this is a plus now, plus 14. I will write plus 14 times 2 equal to 2. Now I'm going to come back and I'm going to count. How many 14s do I have here? 3 of them. Here's 1, and here's 2 more. So I'm going to write plus 14 times 3. And here we have 20 times a minus 2. I keep getting ahead of myself every time I write the 20 there, don't I? Okay, and now compare what we have there with the equation we were asked to find solutions to. Okay, if we let x equal minus 2, look what we got here, 20 times x, 20 times minus 2. Now we'll put x sub 0, because this is just one solution. And y sub 0, we got 14 times 3. And maybe you picked that out. Remember that if there's one solution, there's an infinite amount, but we used the Euclidean algorithm to find one particular solution to this. Okay, I'm going to extend this problem a little bit and say, imagine that I was asked to find 20x, find integer solutions to 20x plus 14y equal to 10. Well, I probably moved it too far. Well, look what we can do on the bottom here. We can multiply this thing by 5 on both sides, and we will have that. That is, if we take 20 and distribute 5 times each of these, we have 20 times 5 minus 10, or 5 minus 2 is minus 10, plus 14, and we're distributing a 5 here, so instead of 14 times 3, let's have 14 times 15 is equal to 2 times 5 and 10, right? So we can solve even more complicated problems, remember, as long as this number is a multiple of the greatest common divisor. So I could find solutions to, well, the greatest common divisor is 2, so any even number over here will have solutions. And once we find them, we can find a bunch of them. Maybe we'll deal with that in the next video if the next video is required. Okay, let's go to a little more challenging problem. (167x plus 422y equal to 37). All right, this is not so easily done as the last one. Well, let's give it a shot, shall we? It's not as bad as you think. Let's first off find the greatest common divisor of these two things, because if it doesn't have if the greatest common divisor of these two numbers does not divide this, then we can't solve it anyways. So let's find out. Let's say that the greatest common divisor of 422 and 167 is equal to, remember what we do here, we're going to take 422 and we're going to divide it by 167. So when you do that on your calculator, you will get 2 point something, and then you will take 422 and you'll subtract 2 of these, and you get a remainder of 88. Okay? That means then that we can say it is also equal to the greatest common divisor of 167 and 88. And we repeat, let's take 167 and divide it by 88. And that goes in one time. This one you could probably do in your head maybe. And when we subtract 188, we get a remainder of 79. And then we repeat. We say, okay, then let's find the greatest common divisor of 88 and 79. That is, we're going to take 88 divided by 79. We can see right away that it just goes in once. And when we do 88 minus 179, minus 179, we're going to get a remainder of 9. Okay? And we do it again. What is the greatest common divisor of 79 and 9? And so we're going to take 79, we're going to divide it by 9. It goes in 8 times, so we take 79 minus 9 times 8, and we're going to get a remainder of 7. And we can do it again. I'm going to make sure that you're seeing what I'm doing here, yeah? We can still see. Okay, so the greatest common divisor of the smaller one and the remainder, 9 divided by 7. Goes in once and a remainder of 2. So we have the greatest common divisor of 7 and 2. We divide again. 7 divided by 2, it goes in 3 times and we get a remainder of 1. And so we can do the greatest common divisor of 2 and 1. And I think at that point you realize, you'll probably agree with me, that we can just stop right there. Because what is the greatest common divisor of 2 and 1? Correct? It is just 1. So first off, does this have a solution? Remember that it will only have a solution if the greatest common divisor of these two things also divides the C term, which is in 37. Well, the greatest common divisor of 167 and 422 is 1, and that certainly divides 37. So there are solutions. So how do we go about finding them? We start right here again. How did we get this remainder of 1, may I ask? Tell me what we did. Oh, yeah, right. We had 7, and we subtracted 3 2's from it. That's how we got 1, right? And so we go back again, and we look at this remainder. How did we get 2 here? That's right. We took 9, and we subtracted 7. That's how we got 2, so we're going to put that into this expression, and I'm going to write 7 minus 3 times 9 minus 7 equal to 1. And now I'm going to collect like terms. So we're just kind of looking at what we have here. We have 7s and 9s and 7s is the next one, so I'm just going to count them. I'm going to rewrite them and count them. I have 7 minus 3 9s, and then this is a minus 3 times a minus 7, so that's going to be plus 3 7s equal to 1. And I'm going to regroup. We had 1 7 here and 3 here, so we have 4 times 7 minus 3 times 9 equal to 1. Okay, and then we're going to go to the next one. What is the next remainder that we had? 7. And how did we get 7 here? We did 79 minus 8 9s. That's how we got a remainder of 7. And so we're going to replace 7 over here with this expression. So I'm going to write it here. I'm going to write 4 times 79 minus 8 times 9. Nope. Yep. That's 7, right? 79 minus 72. Yep. So, and then I have still minus 3 times 9 equal to 7. So, we're dealing with 9s. Our next remainder is 9s. And then look what the next one is, 79s. So we're going to count 9s and 79s. So, I'm going to distribute. I have 4 times 79. This is 4 times a minus 8, so minus 32 times 9. And minus 3 9s. And I'm replacing, I still have this expression right here, and I'm replacing the 7. So this is all equal to 1, right? This whole big crazy expression for 7, I just put it into here. Okay, let's recount our 9s and our 79s. We have 4 times 79 minus 35 9s, and that is equal to 1. So anytime you're doing this, you might as well stop every once in a while and enter this expression and make sure it still equals 1. If it doesn't, you've made an arithmetic mistake somewhere, and that's not hard to do for these things. So the next one. How did we get to a remainder of 9? We're going to replace this remainder of 9. How did we get to 9? We did 88 minus 179. That's how we got a 9. And so I'm going to replace the remainder of 9 with this expression. So we have 4 times 79 minus 35 times 9. But 9 can also be written as 88 minus 79. Equal to 1. So, what are we counting now? Well, we're counting 79s and 88s. We're almost there. Okay? So, how we are going to now... Oh, yep, I got to collect my like terms. So, 4 times 79 minus 35 88s plus 35 79s. And it's all equal to 1. And so let's collect the right like terms again. We have, I'm going to write it right here. How many 79s do we have there? 39 of them? 39 79s minus 35 88s. Okay? And that's all equal to 1. Now, we are going to replace the 79, that is the remainder here. And what are we going to replace it with? What did we do to get to 79? We took 167 and we just subtracted 88. So I'm going to replace that right there. We have 39 times 167 minus 88 minus 35 times 88 is equal to 1. So 39 167s minus 39 88s minus 35 88s all equal to 1. Okay, we go back and collect like terms. We have 39 times 167 minus 35 minus 39 minus 35 is minus 74 times 88 equal to 1. You could check yourself to make sure everything's okay. I can just look at my paper and see. Let's see. 3977. Oh, 39. Yep, we're good. Okay, we're almost there. So, one last one. We have to replace the 88 with, look at, notice we already have 167 there. So what are we're working on now is the 422. So what did we do to get an 88 here? We just took 422 and we subtracted how many 167s? 2 of them. That's how we got to 88. So I'm going to put that into my equation. here's my expression for 1, but I want to replace it with the expression for 88. So 39 times 167 minus 74 times 88. But what is 88? 88 is 422 minus 2 times 167. All that is equal to 1. Goodness gracious. We distribute, we have 39 times 167 minus 74, 422s, and minus 74 times a minus 2 is going to be plus 148. 148 what's? 167s. Whew, almost there, huh? 39 plus 148. Let's see, 157, 187. So we have minus 74 times 422 plus 187 times 167. All that is equal to 1. Let me check to make sure that my paper agrees with that. It does. Now I'm going to rewrite it. I'm going to write it like this. So 167 times 187 is equal to 167 times 187 plus 422 times a minus 74 is equal to 1. Okay? Does it look like what we need yet? What do we need to do to this guy to make it look like this? Multiply by 37. Good. I'm going to get my calculator for that. I've done enough mental arithmetic for 6 days now. Okay, so I'm going to multiply, I'm going to distribute a 37. Or I'm going to multiply 37 by each side, rather. I'm going to distribute on the left side, so we're going to have 37 times 187. 6,119. So 167 times 6,919 plus 422 times, well, I have to take minus 74 and multiply it by 37. And I get minus 2,738. Let's rewrite this. 167 times, uh-oh, I made a mistake here. Oh, no, I didn't. 167 times 6,919 plus 422 times minus 2,738 is equal to 37. I will check on my calculator. 167 times 6919 plus 422 times minus 2738. 37, it works. So, we were asked to find solutions to this thing, and we have them when x is equal to 6,919 and when x is equal, and when y, excuse me, is equal to minus 2,738. Okay? That is Diophantine equations and how you solve them. Pretty remarkable that he was able to do this so long ago. It's pretty interesting stuff. This is a lot of what your computers will do to solve certain things, right? And we can program computers and softwares to do these things relatively easily. It gets a little monotonous, right? But computers are good at monotonous things. We tend to make mistakes the more tired we get. So that is number theory enhancement part 3. Part 4, if there is a part 4, will show how we can do things like just keep generating solutions once we have one. So another interesting thing might be how many solutions does that have where, well, and that one maybe is not a good example. But a lot of them where we can say things like, hey, how many solutions does this equation have where both the x and the y are positive, or where both the x and the y are negative? And that is another level to this. If we're going to do that or not, I guess, depends on how many people get through number theory enhancement part 3, this one. Okay, so I'm going to give you 3 or 4 problems to try to use the Euclidean algorithm to find the greatest common divisor first, decide whether it has a solution, and then once it does, build it back up. Okay, so watch the film while you're doing the problems so you can remember what we're doing each time. I do believe that this will be a little challenging for some of you guys, especially the 7th and 8th graders, but I also believe you're capable of it. Okay, so ask me for help if you need, send me a picture of where you're at, and hopefully I can help you out. I love you. Oh man, that's a long video.